Section 2.3 offers a brief history of atomic theory. While the textbook offers 2 learning outcomes, we've broken it down into several main learning outcomes covering Dalton's theory, Millikan's experiment, and Rutherford's work to explain the early atomic theories. Let's begin. Dalton's atomic theory had 4 main points. First, Dalton proposed that matter is made up of tiny, indivisible particles called atoms. Each atom of a particular element has the same mass, but the mass of an atom of one element is different from the mass of an atom of any other element. Atoms combine to form what we now call molecules. When they do so, they combine in small whole number ratios, and atoms of some pairs of elements can combine with each other in different small whole number ratios to form different compounds, much like we saw with carbon, nitrogen, and oxygen in the last lecture. Modern revisions to Dalton's atomic theory have shown that points 1 and 2 are no longer accurate. The discovery of subatomic particles and nuclear reactions corrected the notion that atoms are indivisible. The discovery of isotopes disproved that all atoms of the same element have the same mass. Dalton's law supported several prevailing theories. The law of conservation of mass demonstrated atoms combine to form compounds, and atoms do not break down and are not built out of nothing. They merely exchange partners to form new compounds. Therefore, mass is conserved during a chemical reaction. The law of definite proportions demonstrated that atoms combine to form compounds in small whole number ratios, and each compound contains atoms of specific elements in a very specific ratio. Thus, all samples of a pure compound have identical proportions by mass. The law of multiple proportions demonstrated that atoms of some pairs of elements can combine with each other in different small whole number ratios to form different compounds. When atoms of the same 2 elements combine in different ratios to form different compounds, if the mass of one element is held constant, the ratio of the masses of the other element must be a whole number ratio. J.J. Thomson applied a strong electrical current to various substances in a device called a cathode ray tube. Different substances emitted identical cathode rays with a charge-to-mass ratio of negative 1.76 times 10 to the 8th coulombs per gram, where 1 coulomb is the SI unit of charge. The energy caused rays to be emitted, and the device allowed the rays to pass through a hole and strike a fluorescent screen at the far end of the tube. The rays traveled from the negatively charged electrode to the positive electrode and could be deflected by an external magnetic field, which eventually led to the understanding that cathode rays are actually beams of electrons. The charge of a single electron was measured in 1909 by Robert Millikan in an experiment in which tiny drops of oil were sprayed into a chamber containing oppositely charged electrical plates. The chamber was then irradiated with X-rays to give the oil drops a negative charge. The lower negative plate repelled the drops. By adjusting the magnitude or size of the electric field, and watching with a microscope to see exactly when a drop was suspended, he could determine the charge on an individual drop. After many measurements, he found that the total charge of the drops was a multiple of 1.6 times 10 to the negative 19th coulombs, which we now know is the charge of a single electron. Millikan used his charge of an electron and Thomson's charge to mass ratio to determine the mass of an electron. Radioactivity was discovered in 1896 by Henri Becquerel and further studied by Marie Curie in the early 1900s. They identified 3 types of radioactivity: positively charged alpha particles, negatively charged beta particles, and neutral gamma particles. These radioactive particles or rays, were quickly utilized to probe the structure of the atom. At the time, there were two prevailing theories of atomic structure: Dalton's model, where the atom was an indivisible sphere, and Thomson's plum pudding model, where negatively charged electrons were suspended in a larger sphere of positive charge. To discover which model was correct, Ernest Rutherford and students Geiger and Marsden tested the Thomson plum pudding model of the atoms in the early 1900s. Rutherford predicted that the positively charged alpha particles would pass through atoms without being stopped because there is no area of concentrated mass or concentrated charge to deflect them. He designed a gold foil experiment to test this hypothesis. In this experiment, a radioactive source was used to bombard a piece of gold foil with alpha particles. The gold foil was surrounded by a fluorescent screen to detect the impact of alpha particles, most of which were predicted to pass through the foil with little, if any, deflection. While most alpha particles did travel through the foil, a substantial number deflected, some even directly backward toward the source. From these results, Rutherford concluded that Thomson's model of the atom was insufficient to explain his findings, since the atom must contain a concentration of positive charge in a relatively small area. The nucleus contains the atom's positive charge and is quite small compared to the overall size of Rutherford's atom. Most of the atom is empty space with small negatively charged electrons spread throughout the space. The number of negatively charged electrons is equal to the number of positively charged particles, called protons, inside the nucleus. In conclusion, other discoveries found that the charge of the proton, +1, is equal in magnitude but opposite in sign from the charge of the electron, -1. Electrically neutral atoms contain the same number of protons and electrons. While studying this phenomenon, Rutherford found that helium has only one more proton than hydrogen, but 4 times the mass. Rutherford hypothesized the existence of another particle to account for this difference in mass, which was explained in 1932 when James Chadwick demonstrated the presence of neutral particles in the nucleus, now called neutrons. As always, I'll leave you with the parting thoughts of the authors.